Dr. Yuding is the Anderson Interface Chair and Professor in the Milton Stewart School of Industrial and Systems Engineering at Georgia Tech. Prior to joining Georgia Tech, he was the Mike and Sugar Barnes Professor of Industrial and Systems Engineering at Texas A&M University. Dr. Dean's research focuses on data and quality science and system informatics. He is the author of the CRC Press book, Data Science for Wind Energy, and a co-author of the Springer Nature book, Data Science for Nano Image Analysis. His research work is recognized by many awards from the IISE, the Industrial Institute's Industrial and System Engineering. Such like 2019 IISE's Technical Innovation Award 2022, Informs Impact Prize 2024, ASME's Blackboard Machine Tool and Gauge Award 2024, SME's SMU Research Implementation Award, and 2024 AISE Energy System Division's Career Achievement Award. Dr. Dean is Senior Vice President of the IISE on International Operations, and he is also the Editor-in-Chief of the Informs Journal on Data Science. Dr. Dean served as Program Chair for the IEEE CASE. CASE is the Conference on Automation Science and Engineering 2025, just was held in Los Angeles in August this year, and the Editor-in-Chief of the IISE Transactions for the term 2021 to 2024. Let's welcome Dr. Dean to share with us his book, Data Science and Wind Energy. Sorry. So please, Dr. Dean, you can share your screen.
Okay, Dr. Lee, can you see my screen?
Yes,
Can
we
you hear
can.
me?
Yes, we can.
Is this a full screen mode?
Yes.
Okay. So you can hear me all right?
Everything is good. You can
Okay.
start now.
Well, thank you very much for inviting me. I'm sorry I couldn't really be in on site to give the talk in person. I was in Switzerland last week, so I was telling Dr. Lee, it's going to be difficult to make another international trip to Mexico, although to Mexico is a lot of closer. I have been to Mexico twice. So the first time, of course, I went to Cancun. So after my trip to Cancun, I came back to, at that time I was in Texas. I was talking to one of my colleagues growing up in Mexico, Dr. Eric Moreno. I told him I went to Mexico, and he said, where did you go? I said, I went to Cancun. And then he said, did you only stay in the U.S., the tourist side of Cancun, or you went out? I said, no, I only stayed on the tourist side of Cancun. And Eric said, no, you didn't go to Mexico. You only go to the tourist side of Cancun. That didn't really represent Mexico. It's very different from the rest of the Mexico. So the second time is when Dr. Lee was the general chair for IEEE case 2022 in Mexico City. I went to Mexico City. That was a real experience, which I was able to appreciate more of the Mexican culture and language, even I don't really speak Spanish. So hopefully there's another opportunity, I can go back and enjoy the hospitality of Mexican host. So today my talk, is centered around the book I published 6 years ago, 2019, Data Science and Wind Energy. But before I get to started, because I'm serving as the editor-in-chief of Inform's Journal of Data Science, I always do one slide to promote the journal. So the Inform Journal of Data Science, IJDS, is a relatively new journal in the family of Inform's publication family, and Inform has 17 journals altogether. So this is the latest edition. It's relatively new. On the other hand, we promise of course we cannot promise accept every submission. We only can promise we do a good job reviewing the paper and in a timely manner, right? We promise a quality review of time. And what do we mean by that, right? Right now the average review time for us is about a little bit over a month. The 90% of the paper reviewed within 75 days. Okay, so hopefully that is to the liking of the authors. And even by the end of the review process, you may not necessarily agree with the decision the editor gave you. Hopefully, by reading the editor's report, the review report, you will agree the review team actually spent the time and paid attention to what you did in the paper, and that way you find that the whole experience constructive, right? The journal is running a number of special issues, and we just closed the submission for the GNAI special issue, but we do have another 3 special issues ongoing, and they all have deadlines in 2026. Digital twin special issue deadline in January 2026, and then there's AI energy special issue in May, and also AI special issue for healthcare in September. So I hope you will consider submitting some of the papers to the IJDS special issue. Okay? So back to my technical talk. So I published this book, 2019 CRC Press book on data science for wind energy. And the beginning of the book, when I was writing the preface, I quoted George Box, who was saying all models are wrong, but some are useful, right? I think that's a very important thing to me, because as an engineer, I was trained as an engineer. It's more kind of engineering data scientist. And I think it's really important we make what we do more relevant to the general practice, right? So that is, if you have the time and read some of the chapters of the book, and hopefully that comes across one of the features to you. And by doing that, when I was publishing the book, I also gathered the data and collected the computer code user book. We make it open access, so it's a free use as long as you give the credit for where the data and the computer code come from, right? And so far we released 1 gigabyte wind turbine operational data. Half of them related to the book, and half of them is an extension data set that we released after the publication of the book. I have one more slide about that at the very end of the talk. Right, so the book actually was organized in 3 parts under one overarching formulation. The formulation is pretty simple at the very top of the slide, and basically said, whatever the response, you need to measure on the wind turbine, right? Be it power production, or the stress or the mechanical load on the wind turbine, impacting the reliability part of the device, and they can be expressed as a probability response, and then further expressed as the integration with conditional response, and also the probability of that wind field. So the X is the input, environmental input, primarily the wind condition, right? So study the probability of X is about modeling the wind field, and it can be used for forecasting. The data science problem need to be resolved very much kind of in the category of spatial temporal analysis. in the middle part of this probability, the conditional probability, condition on what kind of X you are given, and now what kind of response you're getting out from the wind turbine device. This is really related to if the response R is what we call Y as a power response. This is really related to the so-called performance analysis, right? Given this much wind, how much power you can produce. And data science problems very much related to non-parametric regression, conditional density estimation, and so forth. But if the R is related to the mechanical load, and this whole formulation and the conditional response is related to reliability analysis, right? And for that one, for failures, for reliability part, you're going to have some extreme value distribution to concern with, and because it's really the high load which worries you rather than the small load, right? And for doing either the physical observation-based analysis or computer simulation-based analysis, you might need to do things like the importance sampling, and that extend to the fault diagnosis and detection early warning. By doing that, we find there's multiple machine learning problems need to resolve. One of them is manifold learning issues, right? Today, I don't think I have, Dr. Lee said I need to more or less limit my talk within 45 minutes, so I don't think I have enough time to cover all three parts. So I'm going to select one of the problems in part 2 and talk about that, which is really the so-called power curve modeling part, okay? And just as a way of advertisement, Inform is the Institute of Operations Research and Management Science. Is one of the home institute I affiliated with, and they asked me to give a 2-hour tutorial in the spring, and which is online, which I believe everyone can join freely. So I'm going to spend a lot of longer time to talk about some of the data science issues in that tutorial in 2026. Okay, so just in case you don't really have the background about the wind turbine operation, and one of the very important function is so-called the power curve. Power curve, to take it simply, is really a function and is pretty strong wind. So beyond that point, there's a very good likelihood the wind turbine could be damaged. Therefore, they use a mechanical mechanism to stop the wind turbine altogether. So this is one single so-called unit-rate curve connecting the wind speed and the power output. In mathematical terms, you can easily imagine there's more than one input wind speed affecting the power production. Therefore, this is not really kind of two-dimensional curve anymore. It's more kind of multi-dimensional power response surface, right? And then if you count the probability, the conditional density, and it will scale up to a kind of probability response surface. So if you go this way from the simple one-dimensional curve or two-dimensional curve, however you look at that, and to multiple dimensional power curve to the power response surface, or you can go upper to lower and to gradually simplify. The most simplification version is the one we put on the slides, right? It's really the expectation of the Y given the wind speed. It's a unit-rate power curve. Now, how this kind of things will be handled in practice, right? We said that all models are wrong, some are useful, and useful to really kind of the wind production practice, right? The IEC, which is the international standard body governing the power production devices, not only power production, but there are other kind of electronic devices, do have a standard, and the wind power production law basically said the power produced is cubically proportional to the wind speed, and also proportional to the wind density, which is the rho here, and the area, how big the wind turbine is. The CP here is a coefficient, right? If the coefficient is constant, the whole thing becomes really simple. The complexity of the whole thing is really the CP is not constant. The CP in turn is also a function of wind speed, the air density, and also attack angle is related to the wind direction. Okay, so the whole relationship between the wind power produced and the wind speed is not necessarily a cubic relationship, right? It's going to be much more complicated. And plus, you have control mechanism which really kind of can bend the curve as you see from the previous slides, right? They are not really kind of one single function form. At a certain point, the function form changes. Because of this kind of complexity, the IEC standard 61400-12 and recommend a simple data-driven method to estimate the so-called power curve, which we nickname that as a binning method. So if you get the actual operational data from the wind turbine, and the binning method basically said you cut the input wind speed into small intervals. They call it bins, right? So this bin is like 0.5 meters per second. And then you count how many data points, which is really the power output, fall into that particular bin. You know, if you look at the very most right sub-figure, which is really amplified two of the bins, the green one and the blue one, right? There's the green dots and blue dots are the data observed in that particular bin. You just do an average. You do nothing else but simply average. So that green bar and the blue bar are the average of those dots. And you use that average as a representation of your power output for that particular bin. So if you cut the input from the cut in wind speed to the cut out wind speed, you have, for example, 20 bins, and you simply end up with 20 data points. You connect all the 20 data points, and then with a smooth curve. And that is really the international standard method, which is called the binning method. Now, if you look at the physical understanding behind the power production, you will realize that by using this most vanilla version of the binning method, the other kind of physical phenomena was not counted for example, the air density, right, the rotor. So the IEC also recognized that. Therefore, they recommended one of the formula is called the air density correction. So instead of using the raw measured wind speed, they will say, let's do a transformation with the raw measured wind speed and then multiply this formula to relative to the standard sea level dry air density with whatever the density you measured on site, okay? And multiply that coefficient to the raw wind speed, and you have the V prime is transformed wind speed. And the IEC said by using the V prime as the input, you do the rest of the same way, and you're going to get a better, more accurate the wind power curve. So this is really the air density corrected binning method. Another thing is really about the wind direction, right? We said that the CP, the coefficient, actually is a function of the attack angle, which is really related to the wind direction. And not only that, you know, when you have multiple turbines working together, you have something called wake effect. And you have one of the turbines really kind of being affected by the neighboring turbines, the rotation of their blade. So another adjustment in the IEC standard is really identified by the so-called free sector in the wind direction. If you look at the figure here, right, from 0 to 360 degrees around one of the particular turbine, and then if you want to identify how many those kind of directions in terms of the degree, they are really kind of so-called free sector, which is not really under another turbine's wake effect. And versus how many of those kind of directions is really for this turbine in the wake for another turbine. And those with the black box is the so-called free sector. The kind of the white margins is the wake factor. And if you combine all these things together, you find the free sector is roughly about 1/3 of the entire 360-degree direction. In other words, there's as many as 2/3 of the raw data is really kind of in the way. So for the IEC standard, we basically recommend you filter those 2/3 of data, only use the remaining 1/3 of data to do the analysis, right? So the pro and cons of the IEC binning method. The IEC binning method, however simple it seems, is really a non-parametric data-driven method. It's very adaptive, it's very easy to use, and it's, the engineer likes that. They know what goes in, what comes out. On the other hand, the binning method primarily only consider one single factor, which is the wind speed. It does consider the air density to some extent, but it's not very optimal. It's in a very ad hoc manner, right? It doesn't really use the wind direction information, it simply controls for that information, right? They only say you're going to use 30% of the information you originally draw measurement, and then else you're going to eliminate that. For the actual practice for wind operators, that's really not optimal, because for them it's not really optional. They can only operate in 30% of the chances, right? They need the turbine to operate all the time. So if you said you have a model which is only good for 30% of your condition, and they will ask you what happened to the rest of the 60% or 70% of the production data. And therefore there's a very common observation of so-called underperformance. It's like whatever the OEM give the theoretical power curve, and when they actually obtain the actual production data, they find they really kind of doesn't really perform as good as the theoretical power curve tells them it can perform. Now, to the defense of the IEC's intention is not really kind of provide machine learning or data-driven tools for the OEM, for the owner-operator to predict how many wind energy they can produce. Their obligation is really provide a standardized condition where the seller and the buyer, they can have a kind of agreed upon condition to verify the claim from the seller, right? The buyer can verify the claim of the seller, right? And so for that purpose, IEC is doing a fine job, right? On the other hand, that kind of tools, how much useful that can be for the actual production is really still up to the air, right? And this is the situation more than 15 years ago, and it hasn't improved in recent years because of the machine learning methods broadly used in wind industry. But there's still plenty of opportunities for people doing data science and AI can contribute to that particular thing. So if you are working on the data science and AI, you can easily imagine the power curve type of modeling, even multivariate, is essentially a non-parametric regression problem, right? It can be directly regression problem, or it can be density regression problem if you want to predict that it's a probability rather than the point estimate. There are many machine learning methods that can be used. Actually, they have been used. We published the R package, which includes many of the versions, and all the things in the table. AMP is the kernel method, TNA is the nearest neighborhood, one version of deep learning, splines, kernel vector machine, XGBoost, and so forth. Right? This is only a subset of the comparison. We did many other comparisons. Right? So you will find, compared with the binning, many of the machine learning methods, they really make a really significant improvement, right? From an error of the rate of 0.12 for whatever the unit is going to be, and one of the average performance from the kernel method is really become 0.08, which is really kind of almost 50% reduction of that binning method, right? So the NP is also one of our own methods. We published in 2015. We developed the method in 2012. It took some time to publish the result. So for a while, we remained one of the competitive methods for the multivariate wind power curve method. Okay, and the general idea is really use a so-called hybrid additive multiplication. The performance is very adaptive, but it's not very scalable. If you only have one dimension, the kernel is really easy workable. If you have 2 dimensions, it's doable, but 3 dimensions is getting harder, and 4 dimensions, the computation is going to do new, and also you're going to use a lot of data to estimate accurately this kind of kernel, right? So we use additive, we use this basically additive model, but we don't really want to use this kernel method which can capture the interactions between different kinds of physical factors. So we use the 3-component model where the kernel capture the critical factor interactions. And then we use the additive structure to ensure the scalability. So this paper published in one of the specific journal, at that time, like I said, 10 years ago, it remained as the most competitive power curve method for a while. But when we work on this one, we also find a problem, and actually the problem was brought to us by one of the industry practitioners. We do have a lot of good problems, and some of the problems can be generated to a general data science problem. And I want to explain the problem, and I also want to tell you a little story behind how we discovered the problem. The problem is this. Actually, it's a really general problem in data science. If you all do like a regression, you know we have this general model y equal to fx plus epsilon, and we assume epsilon is IID. And that assumption is still true to this very day. If you open any kind of textbook, you're going to find something like that later, right? The question is really what other things are going to be assumed for fx, right? If a linear regression of x is a linear function, if it's a Gaussian process, fx is a function with a Gaussian prior. If it's a spline, it's a spline basis, and so forth, right? If it's a neural network, the fx goes through the neural network function. But the epsilon has remained as IID. It's independently identically distributed. In reality, they are not. They're not IID. Right? The data are oftentimes autocorrelated, especially from physical process, unless you have the time of the data collecting is really kind of being sparse. But right now, the automatic sensor data collection is usually giving data really fast. So when you have the data collected on a really close temporal vicinity, the autocorrelation is almost impossible for you to ignore. If you look at the bottom 2 figures, the left figure, the right figure says, if you have underlying, this is simulated data, of course, to make a point. If the underlying function is a very simple quadratic function, the black line, okay? And then you have the data is independent noise, which is the black dots. And then if you use any kind of machine learning method, try to recover an unknown function, which is the red dashed line, you can do a really good job, as long as the noise is independent. But if the noise is not independent, you're going to tend to overfit. You're going to find your function is more complicated than underlying function, which is really the very definition of overfitting. We call this kind of overfitting of temporal overfitting. Because this is overfitting is not really, this is because of the temporal autocorrelation, right? And some people said, wait a minute, you probably didn't really differentiate the training error and the testing error. No, we do. What I'm talking about here, the overfitting error still comes from the actual sample error, right? We have a new x, we have new y, we test on that things. We use that to select the model. It doesn't really entirely get rid of this temporal overfitting problem, okay? And here we use the 2 figures to demonstrate there's the situation we call the in-temporal test error and out-temporal test error, right? One of the, on the left-hand side is the in-temporal test error, is the data was being randomized, the split with one set of training data, another is kind of test data is hold up, right? When you do the model fitting, you use the training data, doesn't really see the test data at all. And then you're going to use the test data to do the model selection and the model evaluation, right? This is really a very standard way of doing cross-validation and this kind of things. Another way is that, you do have a longer period of data, you have the current period, and you do cross-validation whatever in that period, select the data, you're going to use independent the test data from the future period to do the testing. This is the outer temporal test error. There's a difference between these two different things. And how do we discover we actually the term of the machine learning model doesn't handle this kind of problem very well? It's because around 2017, 2018-ish, we run one of the case study with Milton within the company, not a liberty to diverge which one company that is. And they asked us to train a power curve model using their 2015 data. I believe it's 2017, that's why they have 2015 and 2016 data. They give us the entire year of 2015 data, both of X and Y. Okay, they said we train the model. Okay, we're going to use the 2016 data, half of the year, to test on your model performance. Okay, and then to do your RMSE or MAE, they give you pretty much consistent result, right? So the table to the right bottom indicate what we did at that time, right? We use a 5-fold cross-validation and compare with multiple options and to the beginning, and we find our NLP method actually can achieve almost a 30% the error reduction as compared to beginning. And when they give us the test data error for 2016, and by applying to that model, we find none of the data science model we trained really outperform the beginning method. Okay? They are either 4% worse or 15% worse, depending on which model you're going to use. And that was a surprise to us. And that is also really kind of humiliating to us, because we think we are the data scientists, and then it turns out to be we overlooked something, right? The things we overlook is really that fundamental assumption. The IID is not IID. Okay? So we actually started working on that one. We had a paper more or less ready in early part of the 2021. And when the paper was under review, we come across another paper which provides some useful explanation. The paper is a pretty theoretical paper from Journal of American Statistical Association. Not our paper, but it's relevant paper. They use a relatively simple model to explain the phenomenon, and they use a linear, the mixed model to explain the phenomenon. So they said, okay, suppose we have a model with a fixed effect, random effect, and IID noise, right? If you don't really know that, the third and the second term sometimes they combine together, you create a kind of noise which is not IID anymore. You create a kind of correlated noise. And if you don't really know that, and you're going to use a linear predictor, and which is really whatever the y you observe, you have a matrix is a linear combination of whatever the y. You do that as the prediction. Their major conclusion says, okay, the regular cross-validation error is biased and need adjustment. And that adjustment is really the test error estimated by the regular CV plus additional term. The additional term is pretty complicated, right? The additional term has two more terms. One is the correlation among the y's, another is the correlation between the training and the test error, right? So if we think about the two scenarios I just mentioned, one is the in-temporal test error, another is the out-temporal test error. For the in-temporal test error, and the correlation with additional terms, because they come from the same time period, the temporal structure, even we don't really know exactly what they are, is unchanged between the training and the test data set. And that gives us a suggestion these two terms are more or less the same, so they cancel each other. And therefore the CV correction versus the CV, they are more or less is exchangeable. And if you use a cross-validation to do the model selection under this kind of circumstance, you're still doing fine, okay? But if you have the outer-temporal test error, and you will find the second term, the third term of the whole equation, which is really this training and test part, except for the very neighborhood between the future data and the training data, is non-zero. Otherwise, once you outside certain kind of range of the training data, your correlation between the Y training and the Y testing is going to be zero. If that part is a zero, that means the CV correction is going to be the regular cross-validation plus a correction term, which is real hard to estimate. Okay, you know you're going to be biased, but you don't really know how much you're going to bias. And that's the fundamental problem and why this kind of things happen, right? When you use the CV itself to do a model selection, you tend to be biased. You select the wrong model. Okay, you typically select otherwise complicated model you don't really need. Okay, so our model, we come up with one of the methods called TempGP. It's a temporal Gaussian process model to handle this kind of issues. Our solution process actually is relatively simple, right? We also want to decompose our model into two parts, three parts if you count the epsilon, right? The f(x) is the time invariant part. X itself is time invariant, but f(x) the function we hope is time invariant. And then there's a temporally uncorrelated stochastic process. We call it GP. We want to separate. The bigger question is really how can you separately estimate f(x) and GP part, right? And the way we're doing that is we purposely to thin the data. We thin the data enough. The data after the thinning become autocorrelated. So when you apply the uncorrelated data to estimate the model, the GP part is just the zero, and then you estimate is f(x) part. And once you estimate f(x) part, you use the y minus f(x) to use the residual estimate the GP, and you basically do the two-step procedure and to estimate both of the model component, right? There's one of the critical parameter you need to use is how much you need to thin the data. Therefore, you can reduce the autocorrelation to a negligible degree, right? For this, we use the partial autocorrelation function to do until the 95% insignificance, right? So this you can, once you have the data, you can either calculate the P, or you can do a kind of conversion, right? So what happens if we use the TempGP to this 2015-2016 case study? You can find the TempGP when they are applied to the 2015 data itself actually further improve the performance of the other machine learning methods, right? Right now it's 46%. Their improvement on the 2016 data is a really minor, right? But nevertheless, it's still further reduction from beginning. If you look at the other machine learning method, they actually is reversible of, it's an increase of the error relative to beginning. But the TempGP was able to maintain a consistent improvement performance relative to beginning. Right. So this is we into the further analysis on the same 6 data sets we showed earlier, and you see how the TempGP compares with the rest of the machine learning method, and apparently they have pretty consistent performance. One of the issues of the GP, the Gaussian process, is relatively slow computation. And for a data set over tens of thousands of data points. So in the past year or two, we were able to speed up that whole process, right? We use the vacuum approximation method, try to speed it up, and right now they can do the whole computation, even for 1 year worth of data within a couple of minutes, the accuracy deterioration is only about 1%, okay? The power curve actually is a very important foundation for the whole pipeline of the turbine performance quantification. They answer more as the first question, what kind of variable you're going to use, which is really power curve modeling. The second one is, you're probably going to have some kind of selection of data, and for you to control for unwanted the noises or disturbance, right? And then you have the quantification part, how you're going to quantify the effect of an upgrade and also uncertainty associated with that quantification, right? So we were able to do all 3 of them, even though I spent most of the time talking about the first step, right? So just to quickly give you an idea about the second and the third question, the Q2, we invoke one of the old idea from color inference, and this the first version of that idea was presented by Don Rubin himself in 1976, 73 papers called the correlated matching, and if you look at the figure here, right, one of the issues, sometimes you kind of mess up with your estimation of the turbine performance change is really because of the input are very different, right? This wind speed before and after, they have different profile. The temperature, which is related to the air density before and after, they also very different, right? So in order to for the power output, which can be reasonably attributed to turbine's performance, not the environmental change, what you need to do is really make the input, the environmental input probabilistically compared with each other, right? So once you do this kind of color inverse procedures, you can find that the wind speed and the temperature with the probabilistic distribution, they are more comparable. They are not really identical, right? They are just with the whole portfolio, they are more comparable with each other, and therefore the difference between the before and the after the certain kind of technical action, the delta energy can be attributed to the turbine's own change. And all the things we do here, they are data-driven method. We base on a lot of assumptions. We base on assumption of the functions, and therefore we want to quantify how much difference, and also we want to the difference between the comparison, which can show the way the noise part, and therefore to be statistically significant. So we use the Gaussian process as a baseline to come up with uncertainty quantification procedure. And here you can see the blue curve here is really the difference between these two power curve functions, right? And then we calculate the 95% confidence band. Anything above the 90%, which is the blue shade, is a so-called statistically significant difference. If you accumulate this difference, it means it's beyond the random noise, right? And that is more certain for you to claim is due to the engineering action rather than to just a random effect on the ground. So this is the last, the third component, the effect and the certainty quantification part, and try to handle the random noise in the data and also in the model, right? So we did a simulation study because for this kind of analysis, it's really hard to do the physical experiment. If they can do the physical experiment, they probably don't really need a data science method to quantify the uncertainty, quantify the effect. So in order to have some kind of sense how accurately you can recover the turbine performance change, and we did a simulation study. The simulation study is to add certain kind of factor of change to existing data. So we know how much change we make, right? So on the first column, on the first row, is 2%, 3%, 4%, and so forth. But we don't really apply that uniformly to all the data points. That would be too easy, right? And we apply only to those data points corresponding to wind speed greater than 9 meters per second. And then there's the effective how much change for that particular given data set, right? And that's the second row is R prime. So R prime is 1.25. You calculate for that particular data set because depending on how many data points will have greater than 9 meters per second, right? There's a different kind of version of the method, and being applied to recover that underlying true upgrade effect. And the one we used for the new power curve modeling plus correlated matching plus uncertainty quantification consistently deliver a kind of recovery of the true value within 10% of the errors. It's very difficult to exactly recover the things. So 10% is the best we can do at this moment, right? So in the past 10 years, we also did many of the case studies in industry. Like I said, I really admire what George Box said. All models are wrong, but some are useful. In order to be a model to be useful, I believe you have to work with the practitioners directly, right? So the first thing we did actually more than 10 years ago is a blind study with the EDP in North America. And why they want us to do a blind study? Because they don't quite trust the data scientists. they don't really know what you're doing with all the data, right? What data goes in, how you're going to manipulate. Did you really kind of just produce an outcome, a conclusion to please them, right? So they want to know, whether or not you're overfeeding your data. You just kind of manipulate it in a way, and you want them to hear the conclusion. So of course, they don't really know exactly what is the true upgrade effect for their turbines. Like I said, they cannot do physical experiments, but they can do other things to test us. So what they did in that particular blind study is they gave us 3 wind turbine data. And then in one of the turbines, they made actually a technical change to that turbine. They believe that technical change will lead to some of the difference. But they didn't really tell us, before they gave the data to us, they didn't really tell us how many turbines they made that technical change. Of course, they didn't really tell us which turbine they made that technical change. They asked us to tell them how many turbines gone through a technical change. And if there's a non-zero version of that answer, and ask us to tell them which turbine has been changed. Okay? So they give us 3 data sets. Of course, the answer, there's 4 possible answers, while 0 is also answer. Even they said they made the change, it could be they didn't really make any change to any of the turbine. Right? So it's 0, 1, 2, 3. And also we need to tell them which turbines has gone through that change. So after done analysis, we were able to identify one single turbine has been gone through that change, and we tell them specifically which turbine that was. And it turns out our answer was correct. Okay, so that was a huge relief to me. I was pretty nervous in that 1 month period when we were doing the blind study, because I cannot really be 100% certain we were right. Okay, and that really opened the door and earned the trust with the wind professionals, and afterwards we did multiple other studies with Smart Blade, is a small company in Germany, and the EDPR, this headquarters in Madrid, and Goldwind in China. That's for different kind of issues, but very similar analysis. And then later on with Viken, Wind Energy Institute of Canada, we're still working with Viken enough. If it's not because of the U.S.-China the policy, we probably will still be working with Wind in China as well. Okay, so last 2 slides is really, for the data science AI for wind energy. One of the big issues is where you find the data, right? If you don't have the data, how are you going to do the analysis? So we thought about that. I decided to release the data we use in the book. So on the left column is the 10 data sets used the book, and then after 2019 we published the book. We continue to release the data whenever we possible, right? The latest release is the generated failure data set, and we worked with Viken. They are very generous to allow us to release that data. And some of the data is pretty unique. I don't really think you're going to find this kind of data elsewhere, right? For example, the turbine data, associated with the publication of the IEEE transaction on sustainable energy. I think that's probably the only data set you have both of the terrain information and also the wind operation information, the wind power production information in one single data set. So it's I invite you to give it a try and to see what you can. I'm sure you can do great things with those data. Okay. And I also sit on the IEC Wind Task Force 43 on digitalization as one of the effort I led that Wind Task effort for collecting the open data source in the catalog. So we put that on one of the IEC Task Force website, which we don't really own the data, but we get one single stop. You can go through all the data, and most of the data, they are open access, and of course the DSWE data set is among this list of data, but it is a much richer data set of that, and you can take advantage of. So with that, I will stop here, and if I can answer some questions, I'd be pleased to. there's some references. I will send the slides to Dr. Lee afterwards, and she can distribute to the conference workshop attendees.
I'm here. I'm here. No. I'm not. Thank you so much, Dr. Dean.
Thank you.
Can you hear the applause? No? No. Thank you so much. Can you hear? Ahí se puede ver. Thank you so much, Dr. Lee.
Yes,
You hear now.
thank you.
Thank you so much for the so intensive knowledge and information for us. I think we need to replay this video to learn a lot, especially to download your package and the data science, because we also do forecasting wind energy. So let me ask the public if they have any questions. So can you hear? No?
I cannot hear. I cannot hear the last sentence very clearly.
You cannot? Valente? 有人求证一下 Valente。那你过来一下。Pregunta Valente. Algunas preguntas sobre la plática.
Hi, can you hear me?
Yeah, thank you.
I have one question about the environmental variables. How many environmental variables did you use, and how did you select to make the univariate?
So there's it really depends on how many measurements you have in your on the field, right? So there's a very common measurement of the wind speed, wind direction, temperature, pressure. There's a different kind of measurement about the so-called wind stability, like the turbulence intensity, like the wind chill, which is a vertical. You can also measure in the horizontal. Sometimes, well, most commonly measure on the vertical ones. In the book, we share the multiple data sets. Generally, they have either from 5 to 7 this kind of environmental measurement. Sometimes you can have more. You can create one of the variables which may not necessarily in the raw measurement. So we typically don't really down select. We use whatever we could possibly have, right? And then we use the machine learning model. Like we said, there's 3 different components. The first one is which variable is more relevant. So that model, power curve model itself, try to answer that question, right? So when you start with, you use all of them, and then you try to select which one is really most relevant. Sometimes, when we did a lot of analysis, we realized the wind speed is always there, because the physics really make sure the wind speed has to be there. So the temperature almost always there, right? And the wind direction most of the time also there. The other variables come and goes. Okay, sometimes certain kind of variable is significant in other data. Wind farm, other data set, they are not shown as significant. So those kind of things need to be adaptively selected based on its circumstance. Right?
For example, in the power curve, how many turbines do you use to predict? Or just one turbine and one power curve? Or how many?
So a power curve usually associated with a specific turbine. It's called a turbine specific. If you use, for example, if you have two wind turbine, right? You use one, either you use the two wind turbine data put together to generate one power curve to use for both of the turbines, or you use one of the turbine create one of the power curve for use for both of the turbine. This is considered as less ideal than you use for individual turbine, because they have different kind of environmental surrounding. The turbine, even they are of the same make or same model, after a number of years of operation, they are not exactly the same anymore. So they have some unique characteristic, which is really to that particular turbine. So the best practice, as long as you could, sometimes you couldn't, as long as you could, use a turbine-specific power curve. If you have 100 turbines in a wind farm, create 100 power curves. Each power curve for one single turbine. Yeah.
Thank you.
Any more questions?
Hello, Dr. King. Thank you very much for your nice conference. I curious about, is there any effect of rain on the actual results of power in wind turbines? If any, then do you have to include any feature in your non-parametric model in order to take into account the effect of rain?
I'm sorry, I couldn't hear the question. The voice is a bit.
I wondered about the effect of rain shower on the actual power results of power in wind turbines. Is there any effect of rain? If so, do you have to include any feature in your models to take into account for the effect of rain? Question.
Okay, I try to understand. You said, I heard of power, and you said if there's any something I didn't capture, and then I heard about feature. So.
He asked about, can you hear me?
Yeah. To some extent.
He wants to know, do you consider when it rains, how do you model?
You ask when is what?
Rain, 下雨.
When is it raining?
Uh-huh.
Okay, and now what is the question?
Do you think about the raining reason or raining factor in your models?
Oh, I see. Right, yeah, so there's a two part of that, right? Number one, when it's raining, it does have certain kind of effect, right? We have actually, so through our analysis, we find the humidity, even in original physical analysis, the humidity is not part of that power production function. It only is air density. But from the data-driven analysis, we find sometimes humidity can play important role in the power production efficiency. Okay, and this, when we discovered that, actually was quite a surprise to people doing the wind production research. But we actually documented in the paper we published in 2015 the humidity. So when it's raining, the humidity obviously is different when it's not raining, right? So that is a big part of that difference. And the raining has another effect. So when a turbine is operating, there's a cumulative dust. And also there's insects smash on the wind blade. And when the insects smash on the wind blade, the debris don't really kind of take off. So when it's raining, actually it will wash off those kind of things from the blade. We make the blade, the air dynamic foil, and to be cleaner and to be consistent, more consistent with the original design. So people sometimes do observe there's a difference after the rain and versus before the rain, right? So those are really kind of the effect after you use this kind of method, you can detect and how much you benefit. Some of the things was not really affected by the raining. I remember there was an experience I was in discussion with one of the company. They actually told us there's a service company come to propose to do power wash for the blade because of the debris, there are other things. This is one particular one from very close to a mining operation. So they have some kind of very dirty dust accumulated on the wind blade and change the aerodynamic foil of the wind blade. And the rain doesn't really kind of clean these things. And so even after the rain, the wind turbine blade remains as inefficient as before the rain. So they said, we want to do a power wash and to get rid of all of the dirt from the blade, and therefore you can make your wind turbine produce more power with higher efficiency. And of course the question is, the power wash is going to cost you. So how much you're willing to pay depends on how much more power you're going to produce after the service. So it's a long question, right? So like I said, the rain doesn't affect the power production issue, and also it has some other effect which may not necessarily come into the physical, the data aspect of that. It only can be detected after the rain happening.
Thank you very much, Dr. Lee. Due to the time, we cannot make more questions. So I hope someday we could have you here physically in this auditorium, and we could have more space and time to interact with you about the wind energy and data science. Thank you so much. Let's show you the certificate. So can you? Thank you so much. So take time to have a rest for your long journey from Zurich. Okay, see you next time.
I will be there next time.
Sure. Just let me know. Okay, thank
Enjoy
you.
the rest of the conference.
Thank you so much. Bye-bye. Para todos tenemos un coffee break.